So this is the full question that we've seen from the two previous horizontal projectile motion examples. It comes from NCEA Level 2 Physics paper from last year, 2011. And we're asked if the ball will go over Ernie's head, or if it will hit him. Yeah, the question actually suggests you begin by finding the horizontal velocity, which is very nice of the question to do that. It starts you on the right path. But what we really need to find out is the vertical height at the time. So we need the time that it takes to cover the distance of the 35 meters from Jacob to Ernie, and using that time we can then substitute it into one equation to find what the distance will be at the vertical distance at that particular time. Now, just before we get started with this, I'll just circle, this is the equation that we're going to be using. If we wanted to plot a graph of vertical distance against time, we would get a very interesting shape of graph. So that if you were to say plot the time every fraction of a second until you reach the full thing, you would end up with a shape something like this, which is your parabola. Now you can do this in your own time. Best way to do that is to plot a table, distance and time, and you set a particular initial velocity. So you have to know what the initial velocity is to be able to perform these calculations and make this graph. But you'll find that for, I suggest maybe use around about 100 meters per second if you're going to do this. Too small and it becomes a little bit tricky and a little bit fiddly, and you have to start using half-second intervals. But this way you can start from 0, go 1, 2, 3, so forth, and you'll get a range of distances that give you this lovely parabolic shape, which is what we've been talking about as the flight path of our projectile motion, horizontal projectile motion. So what this means in relation to the question above is that with the ball going up and over, we only need the amount of time, as we've said, that the ball takes to get from Jacob to Ernie, and then we just have to substitute into this equation that particular time using that particular initial velocity, which is the vertical component of the 24 meters per second at 36 degrees, and substitute that into this equation or find that position on the graph and at that particular time, and we just want to know if the distance is greater than 1.75 meters to do that. So that's an exercise you can do in your own time anyway. I'm going to start proceeding with the question here. First off, we need the time. To get the time, we need to know the velocity, the horizontal velocity. We can use the horizontal velocity. Let's just note down some of the stuff here. So we can, if we're dealing with horizontal here, we can use the initial horizontal velocity, which is constant, and that'll equal 24 cos 36 degrees, and you can go back and find that one for yourself. I'll do the calculation shortly. We have the range, the horizontal distance, which is 35 meters, and we just need the time, which we can just use because there's no acceleration. So since a equals 0, we can just use our standard velocity equals distance over time and rearrange that to find the time, which will give us time equals velocity times distance. So just quickly plugging that into the calculator to find out the horizontal velocity. I can actually scribble out that initial part because it's just a constant horizontal velocity. So 24 cosine of 36 degrees gives us 19.42 meters per second. It's very hard to draw with a stylus on an iPad because they don't come to a point, they're like a finger. Anyway, now we've got, trying to find the time, plug those numbers back in over here, and we have v times t. I'm just going to shuffle that around a little bit, give us some space. The velocity is 19.42, and it's times by 35 meters. That'll give us the time. Whoops, I've just formed a calculation and got things a little bit mixed up. Where are we? Okay, if you've spotted a mistake, you deserve a chocolate fish, as one of my university lecturers used to say. This does not rearrange to form this, so scratch that. You want to make time this subject. Let's just perform this calculation in full because it's good practice, and you can see that even I make mistakes. I'm not perfect. Teacher's not perfect, remember that. This is also a good reason why you should collaborate with others. As per our Facebook page and Google Plus and Twitter feed, other people pick up mistakes that you might not notice for yourself. I'm just fortunate that I've picked up this one. So anyway, rearranging v equals d over t. We want to make t the subject, so we're going to multiply both sides by t. So t times v equals dt over t. This side the t's cancel, and now we're wanting to divide both sides by v. So tv over v equals d over v. So the v's on this side cancel, leaving us with t equals d over v, and that's a bit more like it. Let's just plug the numbers into there. What do we have? We had the velocity is 19.42 and the distance is 35 meters over 19.42. That gives us a time of 1.802 seconds. Notice I'm sticking with this 4 significant figures because it means when later on when I go to round I'm not going to have minor errors due to rounding at an early stage. So 1.802 seconds. We're now, where are we? Let's just go across to the side. We're now in a position where we've got almost everything that we need. We've got the time, we've got the acceleration, which is just negative 9.81. We just need the initial vertical velocity, and that comes from, we'll go this way, why not? The initial vertical velocity is here, and that is 24 sine this time, 36 degrees. And that gives us, I believe if I remember right, it was 14.11, but I'll double check. 24 times the sine of 36 degrees equals 14.11, there we go, meters per second. So now we have all of the information, we can substitute that into the equation and find out what distance we get at that height. So let's go ahead and do that. D equals the initial velocity 14.11 times the time of, I've already forgotten what it was, 1.802 times by 1.802 plus half negative, within brackets, 9.81 times again by the time times by 1.802 squared. Plugging all of that into the calculator. And that gives us a distance of 9.493 meters. So rounding that to two significant figures as with the original data, 9.5 metres. 9.5 metres is clearly higher than 1.75 metres, so we can say quite confidently that will the ball go over Ernie's head? Yes. There we go, and that's the question completed.